used here real quick are these notes here that you will be using for you. They're called Powers of 10 notes. They've got a front that looks like this. It's on your left hand side. It has a chart, and you should have also on the back are 4 questions there and observations that you'll be needing to take and do using the chart after we fill this in together here with us. Basically what we're going to do is we're going to take a look at what are powers of 10. How quickly do they increase? How quickly do they decrease? And why are they important in our lives here? What do they use them for? Basically, just to kind of give you a rundown, this is the lead up to our unit of scientific notation, where we're going to be looking at how we can take powers of 10 and convert into small numbers and convert into large numbers. And so forth, going to there. So what we're going to do first is we're going to show you a quick little video. The video is going to show you how quickly these things grow using powers of 10, and how we use these to represent these huge numbers that we did not know long before in past history. How we didn't have any idea of how big things were, so we needed to use something to help us with those numbers to be able to be manageable, and how we learned about what atoms were in the DNA, and how we had to zoom in and we could use these small numbers using the powers of base 10. So I'm going to show you a quick video to look at those. Then we're going to fill in a few parts of this chart, and you guys are going to fill in the rest there. And then I want you to use your knowledge, your thinking caps, your brains there, and help you try to think you can answer numbers 1, 2, 3, and 4. Alright? If you have any questions, you can ask me or Miss Johns, and we'll be glad to help you. So let me pull up the video here for you. It's a great video. Let me take a look and show you what it is. Let's take a look at it.
Since the universe is a big place, we could easily get lost. So we'll need signposts to give us a sense of scale. The Acrobat's ring is 1 meter wide. The crowd is 10 times wider, 10 meters across, larger by 1 power of 10. Now, with every step, every ring, we travel 10 times farther from Venice, and our view of the universe is 10 times wider. The 100-meter ring surrounds St. Mark's, and 1,000 meters, 1 kilometer, the city center. As our speed increases, 4 steps, 4 powers of 10, reveal all the islands of Venice, the Adriatic Sea, and the mainland of northern Italy. Six steps take in Europe from central Germany across Italy to the Balkans. And soon we can see the entire planet, our home in space. Eight steps on our outward journey, 8 powers of 10, and we pass the farthest reaches of human travel, the moon. If we visualize the paths that the 9 planets take in their orbits around the sun, at 13 steps from St. Mark's Square, the entire solar system comes into view.
That's 10 to the 13th power. There's 10 to the 14th.
15 steps, 15 powers of 10. We can see that our sun is just another star. From here on, our voyage will be measured in light years, the distance light travels in an entire year. Only now do we fly past our nearest neighbor stars, almost 5 light years away. same journey at the speed of today's spacecraft would last 100,000 years. As we cross the perpetual night, our voyage takes us up and out of our sun's neighborhood, near the edge of a great pinwheel of stars. The Milky Way is actually a spiral galaxy, and our own sun is just one of 100 billion stars in it. At this immense scale, 23 powers of 10, each shining light we see is not a star, but an entire galaxy, composed of countless stars. Astronomers have discovered that the galaxies are flying away from one another. The universe is expanding. Our own galaxy, and all the others, form clusters and superclusters of stupendous size, hundreds of millions of light years across. And here, about 15 billion light years from Venice, we approach the outer limits of the visible universe. What lies beyond this cosmic horizon, we cannot see and do not know. While Galileo's telescope allowed us to take an outward voyage, another innovation here in the Dutch town of Delft would lead us on an inward journey of discovery. Over 3 centuries ago, Antony van Leeuwenhoek perfected the early microscope and used it to study droplets from the waterways of Holland. As students today make their own discoveries, imagine the moment when Van Leeuwenhoek peered through his more powerful instrument and discovered a living kingdom in a drop of water. This busy world of single-cell paramecia is only 1 millimeter across, 3 powers of 10 smaller than a meter.
That's 10 to the negative 3 power.
The microscope allows us to continue our journey into the realm of the very small. As we move into the cell nucleus, each new ring now reveals a world 10 times smaller in diameter than the last. Deep within the nucleus, we come upon truly remarkable constructions, long, spiraling molecules of DNA. DNA holds the chemical codes for the reproduction of most organisms on the planet, whether they're paramecia, people, or petunias. Voyaging on, we see that molecules are made of even smaller parts called atoms. The tiny world of the carbon atom is very strange indeed. Its 6 electrons seem to swarm everywhere at once. Now our voyage takes us through a void that appears as vast as the space between the stars. Ahead lies the atomic nucleus, so fantastically small that if the whole atom were the size of this theater, its nucleus would be like a speck of dust. Yet the nucleus contains almost all of the atom's mass, packed into particles called protons and neutrons. And these, in turn, are made of still smaller, mysterious things called quarks. Exploring this, the inner frontier of the universe, physicists wonder if quarks might contain even tinier building blocks of matter.
So there's our video that I just wanted to show you about powers of 10, about how things become bigger, how things become smaller, and how quickly they can, and why it's important for us, especially scientists and others who are using these, to be able to understand what's happening in these worlds. Because it's hard to express small numbers and big numbers and add them and subtract them. So that's why we use powers of 10. So let's explore using the powers of 10 now, using our paper that we have here. Okay, we're going to fill in part of the chart. And then what I want you to do is fill in the rest of the chart. And then take a look at these questions and answer them. Okay, so let's take a look at these here that we've got. So let's take a look at the first one. 10 to the 4th power. Well, we know that we can expand 10 to the 4th power out as 10 times 10 times 10 times 10. It's got 4 tens. Okay? And if I wanted to convert that into standard form, well, I know that 10 to the 4th power is the same as 10,000. That's 1 with 4 zeros behind it. 10,000. So if I take something and I'm going to multiply it by 10 to the 4th power, I'm really multiplying it by 10,000. Okay? I'm increasing something by 10,000 if you think about it. So if I have $50,000 in my bank account, I'm really taking 5 times 10,000 to get 50,000, or 5 times 10 to the 4th power, which is the same thing. Okay, so that's what we're going to be looking at here with these. Now, an exponential fraction, well, how would I write that using a fraction? Well, if I wanted to, it'd be 10, let's say, raised to the 4th power, and it's all going to be divided by 1 on the bottom. And to write it in standard form, it is 10,000 to the first over 1. Okay, so that's our first one. Let's look at our second one, 10 to the 3rd power. Well, what's happening in 10 to the 3rd power? If I had to expand that out, I got 3 tens. That's 10 times 10 times 10. Well, if I want to know is, what is 10 times 10 times 10, or 10 to the 3rd power, the same as in a number that we may know? Well, that's the same as 1,000. That's 1 with 3 zeros behind it. So 1,000 is the same as saying 10 to the 3rd power. Okay? So it's basically saying 1 times 10 to the 3rd power, or 1,000, is the same thing. So if I have $2,000, I could write it as 2,000, or I could write it as 2 times 10 to the 3rd power. Because it's basically saying I'm taking 2 and I'm going to multiply it by 1,000. That's what's happening there. To fill in the exponential fraction, it's going to be 10 raised to the 3rd power over 1. And in standard form, the fraction is 1,000 over 1. Okay? So you can be able to fill in the rest of these right here. 10 to the 2nd, 10 to the 1st, 10 to the 0 power, and make some discoveries of what's happening as you fill those in. Let's go down now to 10 to the negative 1st power. What's happening there? Well, that's a -1 power. And Morgan Freeman, who was the narrator of that video, showed you as we zoomed in closer with the atoms and stuff and got smaller, we started using things to the power of 10 with a negative exponent. And we know by what we did last time with negative exponents, that's going to be a fraction. It gets smaller. So how would I expand 1 to the 10 to the -1st power out? Well, that's simply going to be 1 over 10. What is that in standard form? Well, that's 1/10 Or what I want you to put is equals 0.1. Those are the same. To do that is an exponential fraction. It's just going to be 1, oops, going to be 1 divided by 10 to the first power. In that standard form, it's just 1 over 10. I mean 1/10. So when you do 1/10, when you do something like 5 times 10 to the negative 1 power, you're really taking 5 and you're multiplying it by 1/10, which is, here it is as a decimal, or here it is as a exponent right here. And it works out the same. So if I have 5/10, it's really saying 5 times 10 to the first power. Now, I'll prove it to you here by pulling up my calculator. So if I take 5, I have 5/10. So 5/10 here is written this way. This is 5/10. That's 5/10, or 50 cents. So if I take 5 times 10 to the first power, which is also negative first power, which is written like this, see, I get the same thing. So I want you to think about that. Okay, let's try one more here. 10 to the negative 2 power. Well, how do I expand that out? Well, I know that I'm getting smaller, and I know that it's negative, so I need to change it to a fraction. So it's going to be 1 over 10 times 1 over 10, right? What is that going to give me? Well, 1 times 1 is 1. 10 times 10 is 100. So when I multiply something by 10 to the negative 2 power, as he talked about as he's zooming in to the DNA molecules and stuff, he said this is the power of 3, or 10 to the negative 3rd power, or 10 to the negative 2nd power. He was saying 1 meter shrunk it in by a factor of 100. So if you took a meter and shrunk it in by a factor of 100, what would you get? Pretty much a centimeter, because how many? There's 100 centimeters in a meter. So this is equal to, as a decimal, you put it in your calculator, 0.01. And what would this be as in standard form with a fraction? Right here with my exponent. Let me put negative 2, I'm sorry. And then 1 over 100 written as a fraction there. So there we go. So I want you to be able to fill in the rest of those 10 to the 3rd, negative 3, and 10 to the negative 4th power. So that's what's happening here. These are getting smaller. So I want you to think about what's happening as we get going down, getting smaller. What's happening as we're getting bigger? Why is all of a sudden when we said like 10 to the 6th power, we're already outside of the planet Earth, how big we're getting? I want you to think about how much we're expanding on these. Because when you're 3 steps away from the Venice, we were at 1,000 meters. That means one of those hula hoops was a meter, but then all of a sudden we took 3 steps away at a power of 10. We were already at 1,000 of those hula hoops across, wide. That's how big we were, 1,000 meters wide. That's a long, long way. Then all of a sudden we jump up to 10,000 meters wide. That's 10,000 of those hula hoops, and just in another step. And you want to think about how quickly those numbers get bigger. So that's what after you fill in this chart, I want you to then think about answering these questions. What do you see that is happening with the powers of 10 as we increase the exponent? What do you see that's happening with the powers of 10 as we decrease them? That means when we go to the negatives. What's happening there? What kind of patterns can you see that's happening in these? Number 3 says, explain in your own words why you said what was happening in numbers 1 and 2. So if you told me something, explain to me. Why was it happening that way? What made you think that? Were we adding something? Were we subtracting something? Were we getting rid of something? Explain to me exactly what's happening in that thing in your own words. This is just a best guess. I want to see your observations. Then on number 3, we can use the powers, number 4, I'm sorry. It says we can use the powers of 10 to convert to huge. and small numbers into manageable numbers. So these huge numbers we can convert to numbers we can use to add and subtract and multiply and divide. We can take these small numbers and change them into powers of 10 and use them to work with as well. How would we convert these? 1 million? Let's change this here. Not to 1 million. Let's change it to 10,000. And let's change this one to 20,000. And you got 1,000 and 2,000. You got 1/10 and 2/10. You got 1/1000th, and you got 2,000ths. How will we use the power of 10 to help us write these out? Think about how I said you would do like 2 times something. What would be the power of 10 that would be the correct one to use this? See what you can come up with, okay? We're just an exploring activity today, okay? So you should be able to at least get the chart filled out correctly and possibly get numbers 1 and 2, and you should be able to get 3 with it. Number 4 down here, even though it says 3, I want you to try your best to look at these things, okay? If you have a question, ask myself or Miss Johns to help you, and I believe you'll be on your way. Thanks, guys.